Alright, hi, it's me again. Now, just like I promised, here's part 2 of our universe development. Now, in the first part, we talked about how the Big Bang um, created the matter that we see today, dark matter and ordinary matter. Now, in this part, we will talk about how this matter came together to form the first stars, black holes, and galaxies. Now, the matter that the universe created wasn't didn't spread out evenly because there were denser areas and lighter areas. Now, in the in the denser areas, where the dark matter was more concentrated, the, the gravity of the dark matter started pulling in more dark matter as well as ordinary matter, and the more matter was pulled in, the more gravity um, the, the, now there was more gravity basically as the amount of matter, dark and ordinary matter, increased, so that the gravitational influence, and as the gravity increased, more matter was pulled in, basically giving a positive feedback loop. More matter equals more gravity, which equals more matter being pulled in, and so on. Now, eventually, the normal, normal matter increased to the point where the first stars started to form. Now, these stars were massive. Now, the smallest possible stars, or at least the smallest that we believe may have existed, would have had a mass of about 100 solar masses. Now, as I mentioned before in a previous video, when I talk about solar masses, I talk about a mass equal to the sun. So a star with 100 solar masses is equal to 100 suns, and the largest stars that were existing at that time or forming may have had a mass of about 1,000 solar masses. Let me repeat. The largest stars or possible stars at that time may have had a solar mass of about 1,000 suns. You heard me correctly, 1,000. Now, today, the largest stars possible don't go any higher than 150 solar masses. Yet at that stage, the, the universe will have seen stars up to 1,000 solar masses. Now, today, the largest known star in terms of mass is R136A1 in the Large Magellanic Cloud, which is about 165,000 light years from us. Now, it has a mass of 265 solar masses, but it did not form that size. Um, it's actually part of a dense um, cluster which has a few thousand or so stars, and these stars are so close together that they collide and merge quite regularly. Um, that's how the star may have formed, through the collision and merging of two or more high mass stars. Now, when a star forms, it basically collapses or forms out of nebula. Now, nebula are clouds of hydrogen, helium, and silicates and other elements. Now, when a part of a nebula collapses, it forms a protostar, and depending on the size of this globe, or whatever you want to call it, um, depending on how big it is, um, the star, the resulting star may either be low mass, as in a red dwarf, or high mass, as in Rigel. But the star size is dependent on how massive the nebula is. But when this section of a nebula collapses into a protostar, the temperature and pressure inside it increases until hydrogen fuses into helium. But before then, as the protostar forms and collapses, it starts fusing um, this isotope of hydrogen, deuterium, and this releases quite a large amount of energy. Now, the more massive this protoplanet, protostar is, the more energy is released. Now, the minimum size that a protostar can have to remain stable is 150 solar masses. Now, that's the absolute limit or maximum limit that a protostar can have. Any higher than 150 solar masses, and this protostar blows itself apart before it reaches its full potential. Now, now the reason for this is because the universe today has a lot of other elements that the early universe did not have, such as carbon, oxygen, neon, silicates, iron, basically anything heavier than hydrogen, helium, beryllium, that the early universe saw. And now these elements, these heavier elements, carbon, oxygen, for example, um, they cause the star to fuse. Now it causes changes in the star that a pure hydrogen and helium star won't have. Now, I'm not sure on the exact mechanics on this. Um, I'm still researching it, but as far as my understanding goes right now, these heavy elements have an effect on stars today that did not happen in the early universe, since when the star when the first stars formed, there were just there was just hydrogen, helium, and beryllium, lithium, basically just those four elements. And as far as my understanding goes right now, um, stars that formed with those four elements, they could remain more stable than the stars that we see today, or the protostars, remain more stable during the formation stage, and they didn't blow themselves apart. Thus, they could attain much higher masses than we see today. However, because of their high mass, they went through their hydrogen fuel in less than 5 million years. Now, just like stars today, um, they went through their lives just like any other stars today. Now, as the hydrogen in their cores became depleted, helium started to build up in their cores, because that's where all the fusion occurred. And as the helium increased, the core started to shrink, and as it shrank, the pressure and the temperature increased until the helium started to fuse into carbon and oxygen. Now, now, as this happened, the hydrogen formed a hydrogen fusing shell around the helium core, and then the helium, when it started fusing into carbon and oxygen, it did the same thing. It also it also started to form a helium fusing shell around the carbon and oxygen. Now, the same thing happened with the carbon and oxygen. Now, as the as the temperature and the pressure increased, carbon and oxygen started to fuse into the next heaviest element. Sorry about that. Now, The carbon and oxygen also form this fusion shell, and this process went on until iron started to form in the core, and that was about it. Iron in a star is basically the end of the line for any star then and today, because lighter elements from hydrogen to iron, um, or basically any element that's lighter than iron, when they fuse, they release energy. But for iron to fuse, it requires energy, more energy than what the fusion of iron would give out. Now, so this iron started to build up in the core, and once it reached a certain mass, this iron core or mass would collapse while the rest of the star would blow itself apart as a supernova. However, this supernova or these kinds of massive supernova would be much more massive than any supernova we would see today. Now, in today's universe, a supernova would release as much energy in just a few seconds as what the sun did in its entire 10 billion year lifespan. Now, these supernova would release as much, if not more, energy than 1,000 of today's supernova. Now, when this happened, the elements that it created through fusion, helium, carbon, oxygen, and other heavier elements, up to iron, would be ejected outwards through the universe. Also, the shock wave from the supernova would also start star formation on a grand scale up to, well, we're not entirely sure, tens, hundreds, perhaps thousands of light years away. And you could have seen possibly thousands of other stars forming because of this shock wave from this supernova, which then, when these stars go through their life cycles and go off as supernova, they in turn um, start their own star formation through the supernova shockwaves that they produce. And they also see the universe with the elements that they've created, more carbon, oxygen, neon, silicates, such as quartzes, for example. Basically, the elements that you find in rock forming minerals today. Now, there is another thing that they create, and that are black holes. Now, um, stars on this massive scale with such high masses would create black holes that would have a mass of about 10 or 20, possibly up to 100 solar masses with the larger stars. Now, a black hole is basically an object that's so dense yet so small that it sucks in all forms of light, and the escape velocity is greater than the speed of light, which is why they are termed black holes, because even light can't escape them. Now, when these first black holes formed, um, they basically served as a anchoring point for the formation of galaxies. Now, because they could attract and keep the um, matter around them in orbit, and it would also attract more matter, and as it did so, or as they do so, they increase in mass and gravity, and thus pulling in more matter. At the same time, they create these like gravity waves that we've discovered quite a while back, and these then served as a like a triggering point for star formation as well, because these gravitational waves um, increase the matter, the hydrogen and helium, to the point where dense regions would basically collapse and start formation of stars. And now this cycle of new stars being born, going through their life cycle, creating the elements that we see today, and then exploding as supernova, creating black holes, um, and new stars through their shock waves, basically created a huge amount of new stars, new black holes, new elements, and yeah, the original black holes also formed like an anchoring point for all these stars, the black holes that formed after them, and now as all this happened, some stars also formed neutron stars, and when they collide, they create some of the much heavier elements that normal stars, even the high mass stars, can't create, such as gold, platinum, silver, uranium, for example, because when two neutron stars collapse or collide, they create such high pressures and temperatures that the matter within them basically fuses into the elements that are heavier than iron. Normal stars can't create elements heavier than iron, but when they explode as supernova, some of the elements that they have fused from the original mass of hydrogen then fuse into some of the slightly heavier elements. Now, all this happened in just a few million years because we are seeing galaxies and stars, but mostly galaxies within the first billion years after the Big Bang, and some of these, or all the ones that we have observed so far, are very active in their cores, and that's where the original black hole seed is located, and they are active or termed active because the black holes within their core area is sucking in material, hydrogen, helium, and other matter, and some of this matter is ejected outwards as jets at the poles, because not all matter that gets drawn in by a black hole is actually sucked in into the black hole itself. Most of it is actually ejected outwards. However, before the black hole does so, it heats the incoming material to billions of degrees Celsius, and this produces a huge amounts of gamma rays, X rays, and UV rays, as in ultraviolet radiation and other forms of radiation. And yeah, this is why these active galaxies are termed that. They produce a huge amount of activity in their black hole cores. Now, these early galaxies are quite small and not as developed as we see today, with spirals, ellipticals, um, irregulars, for example, just to name a few. Now, we will talk about galaxies more in the next episode, but these early galaxies are now so far from us that we can only see them in the infrared or heat radiation. Now, also, they are moving extremely fast away from us. Now, we can see that in the light. Now, when something is moving towards or away from us, we can see that in the light. Now it's the same with a car. When a car is coming to you, the sound of it increases, but when the car is moving away from you, the sound decreases. Now it's the same with galaxies and stars that are moving towards or away from us. Now we can see it in the light wavelengths. When when a star comes to us, the light wavelength decreases or becomes bluer, but when it moves away from us, the light wavelengths decreases or becomes redder, and thus astronomers call that the redshift, and that's what's happening with these faraway galaxies. We can see it in their light spectrum. The wavelength is moving into the red zone, so they are red shifting, meaning they are moving away from us. And the longer this red shift is, the further away it is, and the faster it's moving from us. Yeah, that's the what was it called again? The yeah, it's called the um yeah, what was it called again? Um, Not Doppler shift, but yeah, oh yeah, Edward Edward Hubble discovered this redshift, and it's named after him. Um, he was the one who also discovered galaxies beyond our own, such as the Andromeda galaxy, and this effect of the red and blue shift is basically named after him. Um, come, I kind of forgot what the name is, but it's somewhere in the line of the Hubble effect. But I will look that up again. And I will talk up, talk about that more in the next episode. So I hope you guys aren't too peeved off about this. But for now, that's about it. And now I hope you guys enjoy these videos. And if there's something that I need to improve, please tell me so. I really need your criticism, and I really want you to tell me if there's something that I need to improve, which is which is one reason why I put up this channel. The first being is for me to talk about these things. I want to talk about science, astronomy, geology, also the occasional movie review. The other reason is for me to improve my speech As you may have noticed, I sometimes take long to say something. So this is one reason why I put up this channel to help me with my speech because I'm sometimes a bit slow. But please, I want you guys to help me with this. Please criticize me with something that I need to improve. Please, I really need you guys with this. And also, if there's a movie you want me to review, please leave that in the comment section, please. I promise, if there's a movie you want me to review, even if even though I don't have the ability to give the visuals of it, like other movie reviewers do, I will review the movie if you request it. But I can only do that if you guys tell me which movie you want me to review. So the same goes for any science or geological or astronomy things you want me to talk about, like Emily did. So if you have an interest in astronomy, geology, science, you can come to me and we will talk about it. Or at least I will talk about it. And there's actually a lot that I can talk about with this because you can actually ask okay, maybe you can't, but my family and friends can actually confirm this. Maybe I can make a video with my phone with that. Maybe I can post it through my phone, but I actually have a whole library of books and National Geographics and DK books. Um, yeah, that's maybe in the next video I can show you some of the books that I have, but I don't have one on me right now. And but anyway, that's about it for today. Please subscribe, please like if you want to. But that's about it for today. And I hope you guys really enjoy these videos. If you do, please leave a like, please subscribe. If not, please tell me so I can improve the channel. Please, I really need this. Please. Please, I actually really enjoy making these. And that's about it for today. I hope you guys enjoy. And peace out.